Just a couple of things about myself. So my name's Paul. I did my PhD in Denmark with Kasper Hornbeck, where I started exploring tactile perception. Before that, I spent time in Canada with Will Vertigal, working on flexible displays. That's actually where I first met Professor Ishii. Later on, now I moved to Germany and I worked as a postdoc for Professor Jürgen Steindl for some time. And recently I was given the opportunity of starting my own group at the Max Planck Institute, which is like the premier basic research institute in Germany. And this we've started off like about 2 months ago. So everything is very new and very exciting. Typically, oh, wait. Yes. So the last couple of talks that I've done, I kind of, I believe that we should pay more attention to what we're doing when we perceive things, and that we should pay attention to how these things unfold in time. So recently, a lot of my talks have been like trying to engineer the audience to agree with me on these questions. Because what I understand is that you are taking Professor Ishii's class and are all creating your own projects. And because of that, I thought that I'd do something a little bit different and I'd kind of present some of the projects that I've been working on in the last years. And the way I thought that I would do that, apologies, I just want to start a timer so that I know what I'm doing, is I'll talk a little bit about integrating electronics with textiles and electronics with the body. Then I will talk about my work in Canada on flexible displays, which leads me to be interested in touch interactions. I'll talk a little bit about what haptic augmented reality might be, and then I want to introduce this idea of body displays. If there are burning questions while I'm talking, I'm happy to be interrupted. I don't know if that's easily possible. Otherwise, I'll just try to be fast enough so that we have some time for talking at the end. So the first project that I'd like to briefly share was actually brought to me by Cedric, who's sitting in the room with all of you. We had been working on pressure sensors together, and Cedric was really impatient because he wanted to make everything himself, and we had to buy some components from factories. So together with material scientists in Portugal and tinkerer inventor friends from Germany, we created a very easy process of creating functional materials. So basically, I mean, what this is about, there's a monomer called pyrrole, and you see it on the left here, or you see the structure of the molecule. And on the right, you see monomer chains, and these monomer chains are electrically conductive and have some pretty cool properties. And in the paper that we wrote together, well, we show something that I find is kind of magic. So with a simple dyeing process, you can create materials which act as sensors. And you see this glove, it's tie-dyed. This is all very sloppy, but the sensors are really good. And this, I said it's very sloppy. Ooh, this is loud. I said it's very sloppy, and there's intentionality behind the sloppiness because it allows us to use processes which everybody knows for shaping this. So in this case, I believe that's actually Cedric here. I'm not sure. He's unfolding a material, and here's Hannah with string, where there's piezoresistive areas, and then dielectrics or insulators, which were created using tie-dye. So in this paper, we show different methods of using traditional dyeing methods for creating kind of high-tech e-textiles. And something that I really like about functional materials is you can stop thinking of materials or sensors as special purpose things. Like there's not, this is a stretch sensor and this is a pressure sensor and that is a strain gauge, but rather you have materials with properties which change in interesting ways when they are being manipulated, and you can measure these changes electrically. So one of the projects we did, which it was a very small project, but I really liked it. We show how with some kinesiotape that we polymerized, we can create all these different sensors. It's a paper that was published in Augmented Humans. And yeah, and the sensors are kind of really cool. I just want to show one of them. All you do, you just kind of tape it to your body, and then there's some circuitry magic, and you get really nice sensors out of them again. So in the augmented human paper, we explain how to do all of this. We actually really wanted to run a workshop where we all build sensors on each other's bodies, but then COVID happened, so we haven't done it yet. But we'd like to do it. So if anybody out there wants to do it, get in touch, I guess. Now, okay, all of these things, let's see, do I have more? Yeah, so these are just sensors. Like, what do you do with them? Why would you want them? What's interesting about them? And one of the applications for functional textiles that I care about, and that I've worked on a lot with Jared Knibbe, a friend of mine, is this idea of skill sleeves. And a skill sleeve is something that you wear, and it allows you to do something you couldn't do before. The way we kind of imagine this working is for example, if this guy, I guess he's playing, I don't know what chord it is, but let's say he's playing a C chord, and I want to learn to play that chord. I could record the electrical activity of my body when playing it. And then I could maybe play it back on your body using EMS. The way this usually would work is kind of like that. I mean, you start at the very left, you maybe start with one pair of EMS sensors or EMS electrodes, which can sense muscle activity, but also stimulate muscle activity. And then, you can make your hand move. But if you want more fine-grained motion, you'll start adding more electrodes. And as you add more electrodes and electrodes, it gets really, really messy. And at some point, it's completely unmanageable. And you end up with prototypes that you can't use because there's too many cables. So we invested some time into making it more compact. This was our first prototype. It was good enough that we could get very high resolution EMS readings. Sorry, I confuse these terms. High resolution EMG readings. So we could measure what the arm was doing with high precision. And then we could actually play that back. So if you did the symbol, we could activate the muscles that make you do the symbol too. But it still was a monster. It was very heavy due to all the cables. It was very uncomfortable to use. It was difficult to apply. So we got together with a friend of ours, Rachel Frere, who's also Cedric and Rachel and Jared and I worked on projects. And she's a tailor. She makes really cool stuff. And she kind of looked at this and scolded us for doing bad work. And together we sat down to learn a better way of building these highly complex textiles which integrate electronics in the body. So here you see a prototype that we made together with her, where we're no longer sewing things, but instead we're layering them with a bonding method, which is elastic. And the final result was much more lightweight and easier to wear and apply. Then using this method, so the paper that I'm presenting here was shown at TI, and in this paper we kind of show our design process of how we, came from this mess over here to this prototype, which is really clean. And what this prototype does, it assumes you're resting your hands on a keyboard, and then it can type for you. So when you're wearing this, a computer can control your typing. So you become an expert typer for free. Again, we're not so much interested in teaching people how to type, but it's more this very close integration between electronics and the body, which we find really cool, and also between electronics and textiles. Yeah, so that's one area that I've been working on kind of these highly integrated textiles. And I'm going to take a step back to kind of how I first got involved with HCI. This was back when e-ink was kind of a cool thing. And the lab that I worked at the time was one of the first labs to have, or to actually hack e-ink displays in such a way that you had very, very thin tablets. Like these tablets were, less than 1 millimeter thick, which you could use for interactions. And we created these scenarios where the tablets were context aware, and you could, if you would move something closer to you, it would show you information that is appropriate to be shown when it's close. When you move it away, it might show an overview. This was a very cool system, and we demoed it a bunch of times, but there never really was a paper about it. But the reason I'm showing this is these tablets aren't only thin, you also see them bending. Like you can literally take these displays and bend them, which at the time was very radical. I mean, I think now we've all seen bendable displays, but that was kind of new. So when a couple of years later, when flexible displays became more readily available, I really wanted to revisit that and build, a fully functional color device which you could bend, which is this phone called Reflex here. And when I first built it, one of the things that I enjoyed doing is I enjoyed pranking people. I would give them like my very first torn down phone, and I would say, hey, bend this device. Don't worry, it's flexible, you can't break it. And then, then I would do this. And so what you see here is like my very simple screen breaking animation. What you don't see is underneath, there's also a haptic actuator, which gives an impulse every time a new piece of glass breaks. And it was a very convincing illusion. And people, I was like, here's a $2,000 screen, bend it. And people, shit, it broke. But I thought this was really interesting and I wanted to do something with that. So we created a device which used bend as an input method. And with the bend, you could control the device. And we did a bunch of experiments. So we, on face value, we did Fitts law studies. But within the Fitts law studies, we would vary the type of feedback people were perceiving. And I'd just like to play some of that feedback. I'll explain better what we did in a moment. Please, somebody give me a thumbs up if you hear the video. I'm not sure if that works.
You know when you like move a rubber band along a smooth surface?
It's kind of reminded me of like a choo-choo train. It's like it
has like a textured kind of like gradient across it, and so
it feels like I'm bending a plank of wood.
It feels like there's a rubber brush.
So what all these participants are saying, we filmed them doing a Fitts law study. So they're trying to get the target from one target to the other. But while they were doing that, we allowed them to kind of vocalize what they experienced. And what all the participants are talking about are different material experiences. So one of the participants, she was bending this plastic display, and she's saying, it feels like a plank of wood. So what's happening here is, because we're coupling the tactile impulses with the amount that the device is being bent, we integrate these experiences. We integrate the bending and we integrate the feedback into one perception. And we're accustomed to such perceptions when we're manipulating material. So whenever I touch a material, my finger is vibrated relative to what I'm doing. And that's what these people are experiencing here. And that's why they're not saying like, oh, it's a buzzing or it's a rumbling, but they're saying like, oh, it's a plank of wood. And we then, like created some applications with that. And this one, you kind of feel the elastic bending. Then the one I really like.
What's happening? So,
the sound comes so fast. I'm sorry about that. This was my favorite application. So I just have two videos. In the first one, I have some stranger explain it because I find strangers' words always really nice. So let's just go with that.
End, I get a page flip as if on this side, as if I was, thumbing through with the pages. So it's like click, 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 click with each page. And when there's a bunch, it's like.
And I want to give you another clip from a stranger at TI who also just experienced this for the first time. And this was this person's spontaneous vocalization. I thought it was so cool and I was so happy I caught it on camera.
Do the connection. Yeah. Can you make them flip faster? There's some haptic feedback in there as well.
Yes. So okay. And the funny thing is, I also I'm feeling the book. and it's definitely not like flipping through a real book. But my hands are getting feedback, so my stupid brain wants to believe I'm holding a real book.
The reason I find it so interesting what this person is saying, he's saying, I'm feeling a book, but it doesn't feel like a book. But I feel things that I feel when I touch a book, so my stupid brain wants to feel a book. And what I find interesting here is that I believe that if you have multiple modalities presenting the same type of information, that we want to make a coherence. So we want to feel that book. If we have the visual, we have the kinesthetic, we have the tactile, we have a desire to make these illusions work. And that's something, you know, that HCI researchers can really take advantage of. So this is work I did with flexible displays, and I was very impressed by what happened when I gave my device to other people and how they talked about it. I thought this was really fascinating, and I wanted to understand that better. And like I know we're here in company where we don't like pixels, right? But displays do some things really well. And so I found this picture because this is the first laptop that I ever used as a kid. And if you look at this display and you look at this display, or this rendering of the display, like stuff has happened. And this is a really cool display. And these displays, they do a couple of interesting things. And if we zoom in, like, okay, over here we have, you know, like full color, and then we zoom in and we just have these dots and dashes of color. And the interesting thing here is, if I would capture all the light that hits me through the window over there, assuming it would be daytime where I am, there would be ultraviolet, there would be IR, and we just see a fraction of that. But if I capture all the light, there's so much more that we don't even see. But what the display does, it only presents the light to us that we can make sense of. It only presents what we can see. And there's something really interesting with this notion of only representing what is meaningfully interpreted by our perception. So what does that mean for touch? So if you see me touching the stone here, and what happens is as my finger moves over the stone, the fingertip is vibrated, and it's vibrated at all kinds of frequencies. And there's some really cool haptics research that records those vibrations and plays it back, and then I feel like I'm touching the stone. But what we don't know is, what do we actually need to play back? Like, what's the RGB here? What is the information that my perceptive system needs to actually interpret I'm touching a stone? So I built something. This is a device, this is a slider that is designed in such a way that it has as little friction of its own as possible. There's a chemical coating underneath it which minimizes the friction. And then I have a motion sensor and I have a haptic actuator. And as you're moving the slider, I vibrate it at a fixed interval. And this feels like friction. When you move the slider, you feel friction, even though no friction is there. It's kind of like, imagine you're taking a stone, you're taking a stick and you're running it past this fence here. The stick would vibrate at a speed proportional to how fast you're running. But you wouldn't think of it as vibration, you would just think of it as the interaction of the stick with this fence. And in the same way, the vibration that I show when you're moving the slider, you feel it as friction and not as vibration. And I was looking for RGB, right? So I made up the simplest RGB that I could think of. My first parameter was granularity. So how many pieces of vibration do you encounter in a fixed distance? The second one was amplitude. How strong are these vibrations? And the last one was timbre, which describes in the frequency spectrum how this vibration feels, or the frequency of each impulse. And I, you know, like I did a study and we created some graphs, and we can see that in the frequency spectrum, different experiences are perceived differently. All of that's not so important. What's important is that you can actually do that. Like, you don't need to fully model it. You can simply reduce it to something much simpler and still, by varying parameters, get interesting tactile experiences, which people consistently describe. So it's something, it's not like that. Hello? Is that a question? Okay, perfect. So I want to move on to where this is relevant in an application. And then I want to do that, I want to talk about one more thing about displays, which is kind of cool. So here we have a pointer, right? You can imagine we're zooming way in on a display. And this isn't what we actually see. This is what the display shows, but that's not what we see. Like, there's stuff going on where our perceptive system bundles a bunch of different color frequencies and we perceive it as, well, as white in this case. Or over here where there's kind of this zigzag pattern, we perceive that as a straight line. So our perceptive system, it has heuristics on how it interprets things, and what we perceive is not necessarily what we're shown. And this is something which is also true for haptics. And I wanted to explore this a bit further. So in this work, I created textures, but I didn't. Sorry, I see a bunch of movement. Are you guys still with me? Am I still with you? Yeah, cool. So in this work, what I did is I created textures, the same way I did with the slider before, but this time the texture is in the middle of the air. And you see these pointing devices in this picture. They have markers, and I can track them. And as I'm moving them through the air, you feel a texture. And then I looked at how do different ways of moving this change how we perceive this virtual texture. And I kind of had 4 conditions. In the first condition, the pointer would vibrate at the same frequency no matter what you're doing. In the second condition, I created an imaginary wall. And as you would point at that wall, you will feel the friction of moving the extension of the pointer over the wall. The next condition was simply moving it. And the last one was rotating it. So what that means is with simply moving it, you would feel friction based on how you change its position. And the rotation means you feel friction as you rotate the device. This is what it kind of looked at. This was the setup. Visually, nothing was happening. People were using these different settings, and we talked about it. It was an interview study where I looked at what are the themes that people come up with when discussing these things. And here's like a very high level summary, but basically when things vibrate, people say, oh, this felt like a train. This felt like a toothbrush. This felt like a motor saw. For the projected condition, where you move the pointer over a virtual wall, people were very confused. That didn't work well. So sometimes it worked, and then they said like, oh, it feels like friction maybe, but not really. Sometimes it didn't, and they said like, oh, it feels like a Geiger counter or something. But the really cool thing was in these 2 conditions where there was like a simple movement caused friction or rotation caused friction. Because when people talked about it, again, these material experiences happened. So people had experiences like, oh, it feels like the device is heavier to move. Or they would say like, oh, it feels like I'm stirring something. Or they would say, it feels like there's concrete, but it's in the air and I can move through it. And this is the stuff that I think is really fascinating. Why should we care? Why is this relevant? For this presentation, I searched stock photos for augmented reality, and I found these pictures. And I think they're hysterical because you have these people waving their hands around in the air. And like, why would they do that? It's not like they can touch anything there. Nothing is there. What's happening here? I don't know. But it highlights that we really care about, manipulating things with our hands. I believe also, I believe this is the Tangibles lecture series where you're creating things that you manipulate with your hands. We want to manipulate stuff with our hands. So this whole disembodied AR that you can maybe touch, but you don't feel, there's something really weird about it. Um, so when I'm moving around outside, I constantly have material experiences. In this case, there's leaves cracking, there's grass bending, the ground is moist and soft and has a little bit of give. So there's all these material experiences that I'm having. So the question that we asked is, can we add a virtual layer of haptic experiences, and can we create haptic augmented reality? So we built a sandal. I didn't notice at the time, but friends have since said, obviously you built a sandal, you guys are German. Anybody else would have had a more fashion appropriate way of doing it. So I promise a nicer prototype next time. But the sandal does a couple of things. It has haptic actuators integrated in the sole. It has a pressure sensor integrated underneath the sole. And it has a microcontroller which can actuate those actuators and which can sample from the sensor. And then what we do, we have, this is connected to software on the computer. And on the right-hand side, you kind of see the architecture of the shoe. And we have a super fast sampling rate. I don't remember. I think it was sampling and actuating at 1,000 hertz. So as you provide pressure, we can measure that with very high resolution in terms of time. And then every once in a while, for example, Unity can send an update and say, like, change what you're feeling. So in practice, this might look something like this. So on the bottom right, you see a Unity visualization of what's happening here. And the interesting thing is that the shoe is sampling pressure at 1 kilohertz, but Unity only sends information to the shoe at, like, what is it, 60 hertz, something like that. So the shoe on its own can create a virtual experience of compliance. So using the system by providing tactile feedback proportional to the change in pressure on the ground, Dennis in this picture here, he feels like he's sinking into the ground. And in the bottom right, you see there's different materials, but when he switches from one material to the other, Unity tells the shoe, hey, change material. Let me show that one more time. So here, Unity would show the snow material, and now he's on wood, and Unity says, do the wood material, and the shoe on its own does that. Why? Because you need that really high sampling rate for these illusions to work. So what exactly are we doing? So as I was stepping down onto these bushes and things, there's many little cracks and things breaking and things compressing. And this feedback, it is proportional to what I'm doing. As I release, we get this cracking again. And all the feedback I'm getting, it is spot on proportional to the force I'm exerting. That's why we need this really high frequency sampling rate. Wait, where am I going? Yeah, so what are the things we can do? So with the shoe, I showed, okay, we can do like augmented reality haptics walking where we change the ground material. But I've explored all these different things. I've explored bending, I've explored displacement, I've explored pushing. Is there any system behind what happens here? Well, yeah, there is. But first of all, okay, so these are direct things, these work. Then you might also have indirect mappings where, for example, the bending controls the position of a cursor, which controls the haptics, or you have a virtual touch point. These things also work, but they require visual feedback for working. Side note, let's get back to where I was actually going. We can organize these different actions along kind of an isotonic, isometric axis. In the isometric case, I change the amount of pressure exerted, but there is no change in position. In the isotonic case, I move something with constant pressure, but change in position. Now, both things can be augmented with haptic feedback. Both things can receive a level of augmented haptic reality if you want, and they do different things. sorry, I jump around. There's also in between these, there's of course elastic devices. More on that in a moment. And here the haptic changes different things. So if you have an isotonic action and you use augmented haptic AR on them, you can create the feeling of resistance. So I can make the air feel as if it resists my movement. If I have something isometric, which doesn't resist my movement, I can make it feel soft. I can provide the illusion that I'm pushing through it. And in the middle where this meets is something that I have yet to really figure out. It's kind of weird, but with the elastic example, it's kind of both or neither, but somehow the experience quality changes. So back to the quote from earlier, they're like, oh, it feels like wood, even though it's clearly not wood. So this gives you this whole vocabulary of kind of stuff you can do with haptic augmented reality. And I think there's more that we can do. And now, like up until now, all the stuff I've talked about, I speak with it to some level of certainty, and we can get into a dialogue and I can explain things with more detail. From now on, this is the stuff that I'm exploring right now and that I think is really interesting, but that I'm still kind of figuring out. How do I display movement? So I can show you a picture of somebody doing a body movement and you can see what it looks like, but how can I make you feel what it feels like? And if we think about it, we have displays for all kinds of modalities. Like I can make you see what I see by showing it to you on a LCD or whatever. I can make you hear what I hear with this. I can make you, I mean, so touch is tricky because we're still learning how to do this, but there are many haptic displays and I can make you perceive information through touch. Potentially even feel what I feel when I touch something. But what's the equivalent for the body? How can I make you feel what my body feels? How can I make you feel the somersault I just did? Like, is that even possible? And I don't know. But there's many indicators that say this is possible. And like the simplest example I've already shown you actually is the haptic shoe, where I say like, oh, he's feeling like something is soft. And there's two ways of presenting this. The first way is saying, oh, they're feeling that the material is doing something that it doesn't do. The other way of experiencing this or of talking about this is, oh, he's feeling that his foot is moving further than it actually moves. So there is this interaction between, if we're rendering a material, between how the material behaves and how I behave. And there are instances, there are actually a bunch of instances where through haptics, you can make people feel like they're moving in a way that they're actually not, which is really interesting. And this is what I'm exploring with my group at the moment. And I just want to show you 3 projects that we're working on right now in very basic terms, which kind of explore this theme of what's a body display. And I think the first application of such a display, which is maybe very obvious, is, for example, in rehabilitation. And again, like with COVID and stuff, actually, Niha, my PhD student, he was doing rehab and he had to do it remotely. And it was really awkward because it was very difficult to understand how he needed to move his arm. And it doesn't really work remotely. So one of the things Niha has been looking at, and I think Niha is here with us. He's possibly here in the group. Maybe you can turn your camera on and wave or something, Niha, if you're still with us. But what Niha has been looking at is, can we use vibration to render force? And it turns out you can, and probably many of you know these types of vibrations. So if you have a vibration which is asymmetric in such a way that it accelerates very fastly in one direction and then slower into the other direction, this is experienced as a force, as pulling or pushing. So what Niha has explored and what we're exploring together is kind of piggybacking onto this virtual experience of force and using that to help guide movements and help people understand movements. Maybe even we can record my movement and then play back the force required for my movement on your body. So this is one area of kind of work in progress on something which might one day become a body display. Then something that is very close to, I mean, I care about all of this, but what I care about especially is the idea of augmenting proprioception. Why do we need to augment proprioception? Well, we think of proprioception as a sense which tells us how our limbs are arranged, right? And often you will read something like the muscle spindles sample the extension of the muscle, and then the central nervous system calculates the relative position of all the limbs to each other. And that's just not really how it works. Because what the proprioceptors that we have, what they do is we have muscle spindles, which tell us if our muscle is compressed all the way. And we have tendon organs, which tell us if it's stretched all the way. And the purpose of these proprioceptors is to protect the body. So the reason why they're there is so that I don't stretch further than I can and I don't push further than I can. So these receptors, they're really, really good at telling me that I'm at the extreme. They're very bad at telling me, oh, it's 22 degrees, oh, it's 27 degrees. We really can't do that through these receptors. We can do it anyway. Why? Well, because there's mechanoreceptors here which stretch, because I see it, because maybe there's mechanoreceptors here, maybe I hear myself moving somehow. Our brain will take any information it can because it doesn't get it from these cells. It's like it's searching, where's information that I can use, and we'll take this information and use it for forming proprioception. Like that's one of the reasons. I don't know how many of you have tried drawing in VR. There's these really cool drawing apps, and it's really, really hard. And there's two reasons why it's hard. The first reason is all of a sudden it's 3D and not 2D. The other reason is if you're using this pencil and moving it over this textured surface, you can imagine hearing it and feeling it, right? And the sound and this vibration is integrated into my proprioception of my body, and it helps me better understand what I'm actually doing. So something that I've been working on is kind of discretizing space. And as I'm moving through space, providing tactile impulses. And what that does is, as I move my hand, I have additional sensory information that provides me with information that I can use for my proprioception. And I think we can really do a lot here. I think this is like, low-hanging fruit that we just need to sit down and explore this systematically. It's the experience of moving through space and getting a tactile impulse at discrete intervals. It sounds very boring when I say it, but it's a really cool feeling. And then the last thing, which I think is very cool, is there are so many parts of our body that do important things that we don't feel at all. So there's, I believe, upstairs from Tangible, what's her name? There's a young lady working on gut interfaces, for example, and we don't really feel our stomachs unless something is wrong with them, There's so much about our body that we don't know, and can we provide access to that? And I have a postdoc, her name's Courtney Reed, who I'm working on this with. So this is not Courtney, this is Anna Trepko. And when I was a teenager, she was like the biggest opera star in Vienna. And my sister was really, really into opera. And sorry, there's a chat message, just checking that. Yeah, right. My sister is really into opera, and she would force me to go to the opera with her. And the Vienna Opera is really expensive, except if you go in through the back door, and then you can go to the very top. So this is the Vienna Opera House. And I remember listening to Anna Netrebko, and I was standing up there. And I tried to make it at scale, but the PowerPoint doesn't allow me to make something small enough. So this is a massive, massive room. And Anna Netrebko is, standing somewhere where this photograph was taken, and she sings in such a way that everyone in this room can hear it. Now, if you or I would do that, after about 10 minutes, we would stop singing because our voice would break. And if we would do that, every night, we wouldn't have a voice anymore because we would just damage and hurt ourselves. So she has trained her voice to be able to do this. And somebody taught her, and she taught herself. But I don't know if anyone has ever felt their vocal cords do things. I haven't, neither has she, neither has anyone else. So how do you teach somebody how to use their vocal cords correctly? If I don't feel it and you don't feel it, and we don't have a good way of talking about it, like, how do we communicate that? And there's so much going on when we sing. It's not just the vocal cords, it's the position of our tongue, it's how the other muscles of our neck are arranged, how we sing. Sorry. There's stuff going on in our abdomen. How do we display that? Can I make you feel what it feels like when I sing? And this is just one thing where we don't have proprioceptive access to, where we could create it. So what Courtney has been doing is she's been using EMS to understand better what we do when we sing, and to provide singers with a way of reflecting on what they do when they sing. So what I'd be really interested in doing is like taking this information and providing it in such a way that these muscles, which we don't feel, become part of our proprioceptive body, and that we do get access to them. So this is all kind of the work that I think work within HCI, or maybe depending on who you ask, the fringes of HCI, but in my opinion, like really exciting HCI work that we can be doing right now, where we use HCI to communicate in ways that we haven't really been able to so far. And of course, like, if we're thinking about communicating with computers, there's this whole area of, can we use the bandwidth gained by having body displays for interesting computational things? But that's something to discuss another time, because I believe my time is almost up. So just to kind of summarize this whole thing, the stuff that I'm excited about at the moment is, on the one hand, kind of like, how do you manufacture these like really complex e-textile things which integrate with the body at a very, kind of a very low level, in this case, electrical integration with the body. And how can we leverage kind of using new materials for creating body interfaces that we cannot create right now yet? And then can we combine that with stuff we know about sensory physiology and stuff that we know about psychophysics of perception? Is there kind of a place where these things come together? And I think there is this place where these things come together, where we can create interfaces which engage with our body in ways that we haven't done so far. That's really what I'd like to be doing in research in the next years. And if any of you guys end up doing stuff in this direction, like tell me as soon as possible, because I think it's so exciting. Yeah, so let's be able to not just look at this, but let's be able to feel this. Thanks all of you for your attention. I'd love to answer questions and chat about this some more. I don't know if there's space and technical setup for doing this right now, but you can also contact me, and we'll just see where that goes. Thank you very much.
Real good.